Good afternoon and happy Halloween. How's it going? Does anybody have any candy? It's Friday afternoon. Nah, I'm kidding. Hope you all had time to get some candy, some sustenance from somewhere, right? Mm. All right, let's get to it. Where did the class notebook go? Oh, here we go. Okay. Analysis of VRD circuit. All right, so we had stopped here. We discussed dependent voltage sources and looked at the four different kinds of dependent voltage sources. So does anybody have any questions before we move on? Okay. Thing to keep in mind is that many of these are used as models for different semiconductor devices, right? And so if we have like a current control current source or a voltage control current source, for instance, we might be using it as a model for a transistor device or some other kind of device. Okay. All right. So couple of slides on elementary devices or some devices, and then we look at a diode circuit. Okay, biasing of a diode circuit. All right. So first up is the electrical switch. An electrical switch is a binary device. It only has two values. It has only two states. You have all taken 133, right? Digital design, and you learn about the binary number system and how we apply it for design of circuits. So switch is binary in nature. It has only two states. It's either on or off. When it's on, it provides a pathway for current to flow through. When it's off, completely open, blocks any passage of current. Okay, so it's either on or off. Digital logic circuit, meaning logic 0 or logic high. When a ideal switch is on, we can say the resistance is 0 ohms. When it's off, we can say it has infinite resistance. Okay, infinite resistance. Real life switches, of course, are not ideal. And so they have some resistance, even though that resistance could be an order of like, milliohms or smaller, perhaps. But it'll still have some resistance. Okay. Those are mechanical switches. I mean, there are variety of switches available. We can use mechanical switches, just flip on and off, like circuit breaker switches. We have digital switches, push button switches that we have on the wall here. There used to be older kinds. Older kinds were kind of microcontroller based switches. And now we have these wireless switches on there, fancy ones, which are solid state electronic devices. Okay. The ones that we have on the wall, and then you make your way out, you can take a look at it. It has the symbol of a wireless network on it. So it's controlling the lights in the room, but it's wirelessly controlled. So obviously it's not a mechanical flip switch, right? So it requires some electronic circuitry. That's where we are talking about, or that leads us into talking about of semiconductor-based switches. One of them is known as voltage-controlled switches. And these voltage-controlled switches are basically made out of devices, typically like transistors. Transistors can be operated as switches, either in the on state or the off state, meaning depending on the input that we apply at one terminal, the outputs at the two other terminals can be turned on or off. Okay, so this is an example of a microchip. It's a 14-pin microchip. Number is 4066. It's a quad bilateral switch, quad meaning there are 4 switches in this chip, bilateral meaning in both directions. If you look at the pin layout, we can see 1, 2, 3, and 4. 4 switches, 3 pins, 12. And then you have power supply connected between pin numbers 14 and 7. Most of these logic circuits or logic microchips, which are 14 pin, 7 is always ground, and then positive voltage is always applied to pin number 14 without fail. Okay, it's pretty standard. Pin number 7 is always ground. Pin number 14 is the supply voltage. All right. For this particular chip, it accepts input all the way up to 18 volts. But digital logic, if you all remember, digital circuits go from 0 to plus 5 volts. Modern digital circuits go from 0 to 3.3 volts. Hence, it says it accepts logic high input of 3 volts all the way up to 18. Okay. No matter what voltage this chip operates on, the controlling pins can never go above supply voltage. Otherwise, we'd end up damaging those. Okay. It's the controlling voltage that's applied, or the current voltage at any of the other pins cannot exceed the supply voltage that is being applied. Right. Okay. Let's look at an example of a VRD circuit. The VRD simply stands for the voltage, resistance, and diode circuit. Okay, VRD circuit. Now, in this VRD circuit, we have a voltage source, we have current ID, and we have voltage, diode voltage, VD. Since this is a series circuit, the current flowing through the circuit is exactly the same for all three components. So resistor current IR is the same as the diode current ID. Okay, no difference. Okay. Now, diode, again, is a semiconductor device, which we'll look at in 315. For 115, what we are doing is we are simply taking it as an off-the-shelf component and using it in circuits or building circuits. Okay. So before we look at anything else in here, let's look at some fundamentals. So the first semiconductor device that was created and presented in the world was a germanium transistor. This was in 1940s, 1947, I believe. It was a result of the work done at Bell Labs. 3 primary people: William Shockley, Walter Brattain, and John Bardeen. Okay, these 3 people ended up winning the Nobel Prize a few years later for their invention. And in the course of history, I mean, nothing that we are using today would exist without that first step, right? And it's just amazing how far we have come. Right now it's like 75 years, but even just like 25 years later, after the creation of the first semiconductor device, 25 years later, there was a big explosion in the market, meaning electronic devices were now everywhere. Up until that point, vacuum tubes were the de facto electronic device. And then these solid-state devices very quickly came to replace everything, right? So William Shockley came up with an equation to describe the relationship between the voltage and the current that took place in the semiconductor devices. And that came to be known as the diode equation because it was between a P and an N junction diode. Okay, and that equation is given right here. This is known as the diode equation. Let's break it down. Okay. We know diode equation, we know diode current ID. Diode voltage is VD. And there's three other terms in this equation. Primary amongst them is IS saturation current. The saturation current is a very, very small current. It's a result of the manufacturing process. Okay. Typically, this is still listed as like 10 raised to minus 13, 10 raised to minus 14, or 10 raised to minus 15. In the labs, when we perform a experiment, we can typically measure around 10 raised to minus 9, 10 raised to minus 10, like nanoamps or so. Okay, so very, very small. And again, all of this is something we'll look at in 315. Then there is something known as N, which is the non-ideality factor. Because the diode is a non-linear device, right? And so a manufacturer will provide this in their spec sheet. So anytime you buy a diode, you look up the spec sheet, manufacturer will have the non-ideality factor in there. Typically, it's between 1 and 2. For most diodes, we simply take it as 1. Okay, for most diodes, we simply take it as 1. All right. And then lastly, we have VT. VT is thermal voltage. Thermal voltage is further given by the equation kT over Q, where T is the temperature in Kelvin. Q is 1 unit charge, and K is the Boltzmann's constant. And all of these are constants based on the temperature. We can calculate what the thermal voltage is. Okay. All right. And so that's the diode equation. Relates the diode voltage and the diode current. Now, for most diodes and most analyses, what we can do is we can simplify this equation. This equation, typically, we ignore the -1. Okay, just to simplify it. We ignore the -1. And so what leaves behind is ID is approximately equal to IS times E raised to VD over NVT. Okay. Also, if N is not given, we assume it to be 1. And so then we can make a further reduction. And I can write ID is approximately equal to IS times E raised to VD over VT. And that's it. There's 3 terms in there. Okay. So far, so good. Now, if you want to find voltage, if we're from the diode current, we can also flip it. What we can do is take ID on the other side. Sorry, take IS on the other side. So we get ID over IS equal to E. And then take log of both sides. And then therefore VD is simply the thermal voltage VT times log of ID or IS. Okay. And if N was not 1, any other value, if N was given, you'd simply throw the N in there. It'll be NVT times log of ID or IS. Okay. As we will see that in an example just in a few slides. All right, let's take a pause. Let me know if you have any questions. So far, so good before you go into the examples. All right. So we are given a VRD circuit, voltage, resistance, and diode. Voltage in this case is given to us as 10 volts. So let's say Vs, the voltage source, is 10 volts. R is not given. Desired ID should be about 0.05. VD is not given, and we are asked to find an appropriate resistor value. Okay. Right. Diode model is given, and from that model, we can find its values. We have IS, saturation current, RS, and N. Okay. N is 1.5. RS is the series resistance of that diode. RS is the series resistance of the diode. VT, when we calculate using room temperature of 300 Kelvin, we typically get 25.8 millivolts, but for simplicity's sake, we round it up to like 26. So if we use 26 millivolts and we calculate, we take this equation, rearrange it to form VD. In VD's equation, we plug in all our known values. We have ID, we have IS, we have N, we have the thermal voltage. We run through our calculations, let's plug and solve, and we obtain diode voltage as 1.86 volts. 1.86. Okay. Diode voltage VD is 1.86 volts. Now, if diode voltage is 1.86 volts, what does it mean for VR? We apply KVL and we calculate VR, which would be 8.14 volts. So 10 minus 1.86 gives us 8.14 volts. So if VR is 8.14 and IR is 50, we apply Ohm's law to calculate R. And that's it. You obtain a value of 163 ohms. 163 is not a standard value of resistance. So we can use multiple resistors in series and parallel to combine it and obtain 163. If we just want one single value, we use the standard value that is closest to 163, which would be 160 ohms. Okay. So let's take a pause while you review it and let me know if you have any questions. Yes. Good question. So RS is the series resistance of the diode. Okay. Is the series resistance of the diode. It's part of the manufacturer's spec. So when we when we buy a product off the shelf and we look at the data sheet from the manufacturer, it will say N is equal to so and so, IS is equal to so and so. So all of these descriptions, not descriptions, the descriptors that we see here, they are all obtained or provided by the manufacturer. So there's junction capacitance, there's transit time, TT, CJ0. There are a few other things in there. But for the most part, we ignore the RS if you are doing any calculation, and then we just run it. But this is here, we're ignoring it to actually make a point. And we will see that point in just a couple of slides. So everybody get that, the question and the response. Okay. All right, so we obtain the R. Now let's look at a circuit where R is given and we are asked to determine the voltage and the diode voltage and diode current. Okay. Actually, sorry, before we do that, let's look at the SPICE simulation result. Oh, by the way, so all of these examples in the notes, they're already solved, right? So you have the answer, you have the question, you have the answer at your disposal. So students, I would strongly recommend to students that you run through any calculations and any simulations on your own when you're doing your own learning and review. Okay. You should perform all the calculations, see if you obtain the same answer. You should perform the simulations to see if you can obtain the same answers. Okay. That is true for not just this course, for any class that you're taking. So when we run the simulation using the same diode, what do we obtain? We obtain 49 milliamps, and we obtain a voltage, a diode voltage of 2.14 right there. So we took the 160 ohms, we plugged it in, and we ran the simulation. Okay, so the numbers are a bit off. Instead of our design of 50 milliamps, we ended up with 49 milliamps. And instead of our calculated voltage of 1.86, we obtained 2.14. And both those things can be explained by the resistance values. The first is that our calculated resistor value was 163. In the simulation, we are plugging in 160 because that's the standard resistor value. And the second is we are ignoring RS in our calculations, whereas the simulation, it's not ignored. Okay. RS, the series resistance, is part of the diode. We cannot change it. We cannot remove it. We cannot separate it out. It is part of the diode. It's physically part of the diode. We can only simulate it by modeling it as a resistor in series with the ideal diode. So I can perhaps, if I wanted to do a more thorough analysis and have more accurate numbers, I would model RS. And I would have my diode this way. And this would be the actual diode, right? This would be RS, the series resistance. Again, it's part of the diode. We cannot separate it out. Okay. So at the bottom, I want to write down this is a self-driven homework. And no submission. I mean, you can work as a group or work in study groups, it's fine. As you don't want to collaborate, but this is more for if you're doing an in-class activity. Okay. You have enough information to do the simulation, right? All right, let's look at a circuit where a resistor value is provided to us. We have a model of, diode model is provided to us, and we need to calculate ID, diode current, as well as diode voltage. For this, I would explain using iterative analysis. So we have source voltage Vs, we have resistor R, 270 ohms, and we have the diode voltage Vd. Okay, simple circuit again. This circuit, by the way, is the same as the LED circuit that we talked about last class, right? We have an LED, which is a diode, and we are applying a voltage to that LED, and we try to bias that LED so that it, so it doesn't burn out and operates within a spec. So biasing helps us with fixing the voltage as well as the current that is associated with that LED. And it's the same kind of application. Okay. So we apply KVL to generate our equation. When we apply KVL, we obtain Vs is equal to VR plus Vd. Vs is 10 volts. VR is ID times 270. Excuse me. And then our diode equation for voltage, you can write down N Vt times Ln ID or Is. Okay. So what do we see about this equation? This is a transcendental equation. It includes a log function inside. So transcendental equations include exponentials, logs, etc. inside the equation. And sometimes they have both terms on both sides of the equation, and we cannot reduce it. Okay? We cannot simply plug and solve. There is no closed form solution for these kind of equations. Okay, so what we do is we perform something known as iterative analysis. Iterative analysis, as the name suggests, or I should say more iterative calculation. Okay, iterative calculation. And as the name suggests, we go through multiple iterations until we arrive at a final answer. So this is the process. We obtained our equation, all well and good, right? Now, we have no starting point, we have no end point. If it's plug and solve, meaning we just plug in all the known values to us and we solve it. We can't do it here. So what we can do is we take that equation, we choose a starting point, and we run through the calculation, right? With the standard linear equation, our starting point is all the values are given to us, we plug it in, we calculate. In this case, we have no starting point. So we are going to choose a starting point, we perform our calculation, and we obtain an answer. Then we match our answer to our initial starting point assumption. Does our answer match with our assumption? If yes, then we are done. If no, then we plug the result as our starting point and we perform the calculation again. Once we perform the calculation again, we obtain a second result, see if it matches up with our assumption. If it doesn't, we plug that in, redo our calculation, and we keep doing the iterations as many times until our answer matches our assumption at the top. Does that make sense? So before looking at the explanation, before looking at the numbers, does the explanation make any sense? Yes, no, kind of. Okay. All right, let's do this. So we have our equation for VD, right? Just right here. Let's say normal diode voltage is approximately 0.6 to 0.7 volts. But let's choose some random value. In this case, the most random value is 0. Let's say the diode voltage is 0, which is right here. If diode voltage is 0, what is the voltage across the resistor? 10 volts. Apply Ohm's law to the resistor, obtain the resistor current, which is the same as the diode current, ID, right? So we plug that into this equation. You obtain diode current as 37 milliamps. Okay, 37 milliamps. Now we take the 37 milliamps and we plug it into this equation. And we plugged in value for ID in there. We obtained diode voltage as 1.847. Okay, 1.847. From this, we calculate the diode current again. So we obtained 30.2A. We take 30.2A and we calculate diode voltage again. And then we take that diode voltage and calculate ID again. So we are reiterating, we are performing multiple iterations of the same quantities. Let me draw kind of a flow chart. So what we did first was we chose VD as equal to 0 volts. From VD equal to 0 volts, we calculated ID. Okay, let me wipe all of this out, make it easier for you to understand. And that ID was 37 milliamps. So from that ID, we calculated VD. From that VD, we calculated ID again. And from that ID, we calculated VD one more time. And finally, we use that to calculate ID. So kind of 3 steps. And we can keep doing this until a result matches the application. In this case, I'm going to take a pause and you take a look at the numbers. And tell me whether they match up or not. What do you all think? Pretty close. And the answer to that question is yes and no, both. It does match up, and no, it does not match up also. It depends on it depends on our application, depends on how many decimal places we want. If I want 1 decimal point and it's 1.8, 1.8, I'm done. If I want, let's say I'm working for a team, my team lead or supervisor says, no, we want it to match all the way down to the millivolts. then I need to take at least 3 decimal places. So I need to go 8.47, 8.39, then it doesn't match up. Does that make sense, right? So if it's 1 decimal point, 1.8 volts, matches up. 3 decimal points down to the millivolt, no, it doesn't match up. So it depends on our end application. What's our end goal? Similarly, ID is 30.2. Final answer in that third step is 30.22. So again, it matches up to 1 decimal point place, or 1 decimal point. But if I wanted to go down to like, microamps, 3, 4, 5, 6 decimal places, it doesn't match up. So you keep reiterating it again and again until you obtain the final answer, which typically does not take long. Okay. All right. Does this process make sense? Yes. That is correct. Yep. It's kind of like a flow chart. In flow charts, typically they ask a question, then it's like yes or no. If it's yes, then you're done. If it's no, then you do this. And then in the next step again, it's like, okay, yes or no. And then if it's yes, you're done. If it's no, then you go back to the top and then you redo it again and again, kind of like that. So let me use red ink and show. So from VD is equal to 1, 0, we calculated this. From 37, we calculated this. From this, we plugged it into here. And then 30 milliamps, we calculated this. Sorry. And then finally, we obtained the answer and plugged it into here. And so we can keep going until we are satisfied with the results. I would urge students to actually take the same equation, I don't know, create MATLAB or Excel file or something, and just keep doing it and see how far you can go until it matches up to like 3, 4, 5, 6 decimal places. It's a good exercise. Okay. Let me show you. There's only one more slide to go. So let me show you something else. So in our 306 class, which is the semiconductors class that E students take, we are talking about mathematical model for a diode circuit. So my diode equation is here, is VT, VD is equal to VT log of 10 minus VD over 10,000 IS. I have VD on both sides. Transcendental equations can't be solved using just plug and solve, okay? So what I do is I choose a starting point. Choose a starting point for VD. And I have the table in the next slide. This table was just created in Excel. So I have VD, and then I just typed up the Excel equations in the spreadsheet. I plugged in VD as 0 just randomly, just to see what we would get, right? So you plugged it in, I obtained 0.594. Obviously, if I'm choosing 0 and obtain 0.594, my answers do not match. So I need to go back and start again. In the next step, I chose 0.65 just to show what happens if I start off. So I start with 0 and then I start at some other value. And then even though I chose 0.65, I still obtained 0.5923. So I chose 0, I obtained 0.592. I chose 0.65, I obtained I chose 0, I got 0.594. I chose 0.65, I obtained 0.592. Matches up to 2 decimal places, not to the millivolts, but still good enough if I wanted to keep it, right? Then I took the 0.592 and I plugged it back into my third step. calculated and reiterated. Now it's matching up to, let's see, right here. 0.592491. 1, 2, 3, 4, 5, 6. Matches up to 6 decimal places, down to the microvolt. Okay. But I still kept going. And finally, you see here, 8 decimal places where the answer is the same as the input. And that's where I say I want to stop. Okay. So this is a technique known as iterative analysis. It simply means you go to multiple iterations of the same calculation until your answer matches with your assumption at the top. Okay. By the way, I'm assuming your departments have had flowcharts for CPE students on what classes you need to take before you get to semesters. So you all are taking 115 now, 215 in winter, and 315 in the spring. So, and there's a cohort that comes after you who's going to take 115 in winter and 215 in spring. Sorry, 115 in winter next quarter and 215 in spring. But for your cohort, 315 will be offered for the final time in spring. Okay, it's not going to be offered yet. So the last and final time, it's only going to be offered in spring. After that, CPE students will take electronics along with the rest of the E students, which is 3306, which is the class that I just showed. Okay. Yes. V of T is right here. And we take it as 25.6. No, we take it at 26 millivolts. 26 millivolts. So those values are all given. So we just pick a starting point and we start solving it that way. Okay, final slide, which is the LT-SPICE simulation of the same circuit. We run the simulation, and we obtain diode current as 29.6 milliamps, which is not quite what we calculated. We calculated 30.2, and this is simulated. Okay, 29.6 is the simulation. 30.2 is the calculated value. If you calculate the percent error between the two, it comes out to be approximately 2%. And again, it can be attributed to the manual calculation ignoring series resistance RS. And RS is about 6% of, not 6%, 6 ohms. Series resistance is about 2.2% of 270. Okay, so that's the discrepancy. All right. One thing I want to state is that the answer is never wrong. It's always approximate. It's only how accurate we want it to be. How many decimal places do we want to go? 1, 2, 3, 4, 5, 6, 7, 8, 9. This depends on our application. So it's never wrong in that sense. The first few iterations, it's not accurate. But by the time you go to like the third or the fourth step, or third or fourth calculation, the answers would automatically match up. Okay. All right, that's the last slide. And this is where we stopped in the previous section. So this is where I'll stop in this section too. We'll pick up here on Monday, quiz on Monday based on material we have covered this week. And then again, for next week, I'll post a homework. And well, wish you have a happy Halloween. Have a good weekend. I'll see you all on Monday.